Hello everyone. Welcome to episode 16 in the Op-Amp tutorial series, Op-Amp Finite Bandwidth Part 3, Compensation. In Part 2, we introduced the concept of instability in op-amp feedback circuits, demonstrated instability with an op-amp simulated in LT-SPICE, then introduced the concepts of phase margin and gain margin, and how to use Bode plots of loop gain to evaluate the stability of op-amp circuits. Today, we're going to introduce the concept of feedback compensation and identify the difference between internal and external compensation, discuss the general design process for externally compensating feedback loops by using our example circuit from the previous video, and briefly touch on a few more compensation methods. So, compensation. Feedback compensation is the process of making adjustments to a feedback circuit to make it more stable and to improve the response, phase margin, and gain margin. Compensation is an important aspect of using op-amps properly. It can range from very simple methods to very complicated ones. In general, the more gain and bandwidth required for a given system, the harder it is to compensate the system. As we saw last time, due to circuit-level parasitics and capacitive load conditions, even the most stable op-amps can be inadvertently pushed into instability. The goal of compensation is to adjust the feedback circuit's loop gain to have good phase margin and gain margin while preserving the desired closed-loop gain and desired bandwidth. Now first, let's talk about op-amp internal compensation. You might see descriptions on datasheets, especially of older op-amps, that say something like unity gain stable or stable down to unity gain. This is because in the early days of op-amps, they were not internally compensated to be stable at unity gain. So, what makes an op-amp design inherently unstable, and why weren't all op-amps compensated to be stable at unity gain? Let's take a look inside an op-amp for answers. Here's the equivalent circuit of the LM324 from the datasheet. The internal workings of op-amps can be roughly modeled as a differential input stage, a gain stage, and an output stage, along with biasing circuitry. I say roughly modeled because op-amps, especially modern ones, may have more stages or clever tricks that help fix some of the non-idealities, or have other kinds of circuits like VBE multiplier stages that don't comfortably fit into this three-stage paradigm. But the rough model works well enough to explain the basics of internal op-amp compensation. Now we expect a configuration of transistors like this to have a few poles due to the capacitances of the various PN junctions and the fact that the first two stages have above unity gain. It turns out that these poles do not tend to be well separated, which means that the open-loop transfer function of the op-amp, without any sort of compensation, tends to look like this. These three poles produce a phase more negative than negative 180 degrees by the time the amplifier hits 0 dB gain. As a result, it is unstable when used with a closed-loop gain of 1. However, if you set the closed-loop gain high enough, then that attenuates the loop gain by the same factor, and so you can push the transfer function into a stable region. So it could operate at high gain. In the early days, high gain and bandwidth were more important, and as we'll see in a moment, the common method of internal compensation of an op-amp will reduce the bandwidth significantly. And so if you were operating with a low closed-loop gain, you would use external compensation. These days, however, most op-amp applications are at unity or close to unity gain. A few examples are signal buffering, active filters, and transimpedance amplifiers. These all use unity gain amplifier configurations, and so op-amps you didn't need to add additional components to in order to get to work at unity gain became more popular. So chip designers started compensating their op-amps internally by placing a compensation capacitor across the gain stage. You can see it prominently displayed on the LM324 equivalent circuit from the input of the emitter-follower stage to the output of the common emitter stage, which marks the input and output of the overall gain stage respectively. This changes the transfer function dramatically, moving one of the poles to a much lower frequency and moving the second pole to a higher frequency. This is the dominant pole configuration we're familiar with, and the phase from the additional poles only coming into play right near the 0 dB gain crossover point. We see that the bandwidth is reduced significantly in the compensated version from frequency FA down to frequency FB. Chip designers tend to minimize the size of the compensation capacitor so as to keep the bandwidth as high as possible while still keeping good phase margin. Some op-amps are specifically designed to be lower bandwidth and higher stability, like our 808618. Others are designed with lower phase margin to achieve higher bandwidths, but nearly all modern op-amps are designed with unity gain stability. There is an exception to this rule. A small class of op-amp chips are designed to be not unity gain stable, requiring a minimum gain of 2, 5, or 10 for stability. They achieve a much higher bandwidth than op-amps with similar other parameters, and are excellent for applications requiring higher gains at higher frequency. Sometimes these non-unity gain stable op-amps are called uncompensated or decompensated op-amps. We won't talk about these op-amps anymore in this video, though the compensation methods we learn today can also be applied to these non-unity gain stable op-amps. So, internal compensation generates the dominant pole configuration, with a phase margin of usually between 45 degrees and 90 degrees. External compensation involves incorporating additional components in the op-amp circuit to stabilize or increase phase margin of the system. But, since we're already unity gain stable, why would we need external compensation? There are 3 general reasons. 1. Because the built-in phase margin of the op-amp is too low, and we want to have even lower overshoot and or ringing in a given application. 2. The circuit's load or parasitic capacitance causes a reduction in phase at the loop gain's gain crossover, resulting in lower phase and gain margin or instability. And 3. The structure of the overall feedback circuit causes a reduction in phase at gain crossover. This happens when an op-amp is part of a larger feedback circuit that structurally has circuits with complicated transfer functions that add negative phase shifts to the loop gain of the overall feedback system, or when the op-amp is structurally not a flat band amplifier, like a differentiator or a filter. And so the feedback network beta itself applies negative phase shifts to the loop gain. So let's discuss external compensation methodology. External compensation depends highly on the application and the specific op-amp part number being used. In fact, oftentimes the best solution is to simply choose a different kind of op-amp. So in that vein, there are a few things to keep in mind when choosing your op-amp and compensating your system. Op-amps that push the limits of their technology tend to have worse phase margin. What we generally mean by this is that op-amps that try to have a combination of higher bandwidth, have higher voltage rails, and have lower power draw tend to have one or more poles in their transfer function that cause the phase margin at gain crossover to be lower. This is because higher voltage and lower power tend to make the resulting circuit lower bandwidth, and so to combat this, that internal compensation capacitor is sized to be smaller, thereby reducing phase margin to push out that bandwidth as much as possible. For a given op-amp, reducing the bandwidth of the loop gain will tend to increase phase margin and make the op-amp more stable. This one makes intuitive sense, as reducing the bandwidth means that higher frequency poles won't come into play. However, this has the obvious downside of reducing the closed-loop transfer function's bandwidth. Capacitive loading of an op-amp, output, or the inverting input to ground will tend to reduce phase margin and make the op-amp circuit less stable. The capacitive loading problem is a difficult problem to solve at high bandwidth, though most circuits do not need to drive high capacitive loads at high frequency, and there are a few tricks for driving lower frequency capacitive loads. Large feedback resistor values will tend to reduce phase margin and make the op-amp circuit less stable. This is related to the problem of capacitance on the inverting input to ground, as the feedback resistors combine with that inverting input capacitance to create an additional pole in the loop gain. The easiest way to fix this issue for low and mid-frequency op-amps is by reducing the resistor values, though that will increase power consumption. For high-frequency op-amps, reducing the resistor values will still work, but they'll have to be dropped pretty low and may cause a more significant increase in power consumption. Now to demonstrate some compensation methods, let's look back at our 80-86-18 circuit and its loop gain. The method of compensation depends a lot on the required gain and bandwidth of the application. So to better help us see how compensation might be done, let's create some requirements for this circuit. Let's say we need this circuit to have a closed loop gain of 2 with a 0.1 dB gain flatness up to around 100 kHz, no closed loop phase requirements, while still being able to drive the 200 picofarad load. We'll also say we want a robust 60 degrees or more of phase margin and at least 10 dB of gain margin. We don't want to draw too much power, so we'll set a limit on the power consumption of 5 milliamps, not including the op-amp supply current or the load current into the output capacitor. As the circuit currently stands, the loop gain of the circuit has a unity gain bandwidth, also called the gain crossover, of 7.59 MHz, 10.38 degrees of phase margin, and 2.69 dB of gain margin. So we have some work to do on both phase and gain margin. There's also a current draw of only 25.1 microamps or less, so we can increase our current draw a bit without violating our requirements. So first, although we already reduced the 100K resistors down to 49.9K in the previous video, I suspect that they are still contributing a significant amount of negative phase shift to the system, making our phase margin poor. So let's simulate the feedback divider with that parasitic capacitor to see its effect on the loop gain and phase in isolation. So we see that this divider has a pole frequency of about 12.76 MHz, which is pretty close to our gain crossover frequency of 7.59 MHz. We can see that the phase contribution at 7.59 MHz is about negative 30.75 degrees, which cuts a large chunk out of our desired phase margin. So the easiest way to make this pole a non-issue is to push it a little higher in frequency, so that it has less of an effect on phase at gain crossover. If we reduce the resistance by a factor of 10 to 4.99K resistors, that will increase the pole frequency by a factor of 10 and will only draw about 250 microamps of current maximum, due to the 2.5 volt rails, which is well below our requirement of 5 milliamps. Simulating the pole with this change, we see that, as expected, the pole frequency is now 127.6 MHz, and the phase at 7.59 MHz is now about negative 3.4 degrees, much better than before. So making this resistor change has mostly negated the effect of the parasitic input capacitance. So, looking back at the loop gain plot with this adjustment made, the gain crossover is now 8.38 MHz with 34.29 degrees of phase margin and 12.73 dB of gain margin. Now that we've gotten that out of the way, let's pause for a moment. We note that the gain crossover is over 80 times the frequency we actually need the system to work at. This is good because it means that the poles that are causing our instability are at a much higher frequency than the bandwidth we need, and so we can incorporate modifications to the circuit that only affect the system at those higher frequencies. We can even make tweaks that affect the closed-loop gain function, so long as those effects only occur at frequencies above 100 kHz. The next compensation strategy we'll employ is called lead compensation. In this case, it involves putting a capacitor on the top resistor of the feedback divider. This introduces a zero-pole pair in the loop gain. The best way to understand how this affects the transfer function is to just simulate this feedback network, beta, in SPICE and examine the frequency response. Here's the feedback network in SPICE and the resulting Bode plot of the divider output using a 100 picofarad test capacitor. At low frequencies, the divider ratio is negative 6 dB, which is equal to 0.5 volts per volt, which is what we expect from this divider. At high frequencies, the gain is unity gain, or 0 dB, which makes sense since the capacitor is effectively shorted at high frequencies. The important piece of this is the phase. We see the phase go from 0 degrees to a peak of about 19.5 degrees at 451.06 kHz due to the zero, then back down to 0 degrees as the phase shift of the pole cancels out the phase shift from the zero. As the phase is positive, this is a phase boost, which if placed near the loop gain's gain crossover point, will increase our phase margin. The amount of phase boost we can get out of this method is dependent upon the non-inverting gain. The lower the non-inverting gain, the more close together the zero and pole are, and thus the lower the phase boost. The higher the non-inverting gain, the further apart the zero and pole are, and the higher the phase will be, up to a maximum of 90 degrees for the case that the zero comes into full effect long before the pole starts to significantly affect the phase. If we size the capacitor just right, we can locate the peak of this phase boost in frequency space right around the gain crossover of the loop gain transfer function to add 19.5 degrees of phase margin to our system. Due to the slight increase in loop gain, it will actually push out our gain crossover slightly. So we should size the boost for slightly greater than 8.38 MHz, so maybe around 10 MHz. The algebraic values for the pole and the zero are shown in the lower right. We can see that the pole frequency is always higher than the zero, and that the separation between them is dependent upon the difference between R1 and R2 as expected. So since we know that the pole and zero frequency are both proportional to 1 over C1, we just have to scale C1 down by 451.06 kHz divided by 10 MHz, which produces a value of 4.511 picofarads. This is pretty close to the standard value of 4.7 picofarads, so we'll use that value. Now looking at the Bode plot of the version with the 4.7 picofarad capacitor, we get a peak phase of 19.5 degrees at right around 9.6 MHz. Fortunately, the phase boost is wide enough to accommodate the error in the capacitor value. The phase boost is greater than 19 degrees from 7.62 MHz up to 12.08 MHz, so it should work pretty well without having to use non-standard capacitor values. We'll note that this actually changes the closed-loop gain function of our system and makes it unity rather than a gain of 2 at high frequencies when the capacitor is shorted. However, this only comes into effect when the loop gain is already near unity, and so the ideal gain is already collapsing. Furthermore, it doesn't violate the gain requirements within our required bandwidth of 100 kHz. You may note that we have neglected to include the 0.5 picofarad parasitic capacitor across R2. We can do this because we successfully pushed that pole out to a much higher frequency, and thus we can ignore it and still get a pretty good approximation of the transfer function of the feedback network. This is especially true since we're not solving for the optimal value of the lead capacitor, just getting close and verifying through the loop gain simulation. So back to the overall circuit's loop gain. Now with this lead compensation installed, the gain crossover is now 10.37 MHz with 47.26 degrees of phase margin and 16.36 dB of gain margin. We still need about 14 degrees of additional phase margin to meet our 60-degree value. So, what's next? One thing the requirements we provided do not stipulate is an output load current or resistance, so we can assume that the only load we need to drive is the 200 picofarad capacitor. Perhaps the cable is connected to a high impedance input at the end, and so the only real load is the 200 picofarad cable capacitance. As a result, all we need to do is to isolate the op-amp output from the capacitor at high frequencies and keep it not isolated at lower frequencies. With the tweaks we've made thus far, the gain crossover now occurs at a frequency 100 times greater than our maximum user frequency, so we should be able to accomplish this. This method is simply putting a resistor in between the op-amp output and the capacitor. This obviously has the immediate drawback of making the signal have a non-zero impedance value in our 100 kHz passband. However, this is often acceptable, especially if the load is capacitive like ours. So we're effectively creating this circuit. Here, the op-amp output resistance is represented by R3 with a value of Z out. The isolation resistor we're going to put between the op-amp and the capacitor is R4 with a value of R iso, and the 200 picofarad capacitive load is C2. I've drawn in the divider because it slightly alters the transfer function by effectively being in parallel with Z out. However, if we assume that Z out is much smaller than 4.99K, which is a valid assumption, then we can ignore its effect on the isolation resistor compensation and treat the divider's effect on loop gain and the isolation resistor's effect on loop gain separately. Assuming Z out is purely resistive, the transfer function of this circuit for Vin to VFB1 has a pole at 1 over 2 pi times the quantity R3 plus R4 times C2, and a 0 at 1 over 2 pi times R4C2. This transfer function directly incorporates this pole and 0 into the loop gain transfer function. This kind of compensation separates the op-amp circuit from the load, and so this isolation resistor introduces a 0 from the perspective of VFB1, which is the op-amp's output pin, but from the perspective of the capacitor, which is the true output, that 0 is not present. And what R iso has done is decreased the frequency of the pole that was made by R3 and C2, and thus reduces the bandwidth. So while this circuit introduces a 0 in the loop gain, it does not introduce that 0 in the effective final circuit transfer function, and indeed pushes the pole to a lower frequency. And it also increases the output resistance of the circuit, which can be undesirable. So the cost of compensation for this method is lowered bandwidth and increased output impedance. To properly decide upon a value for R4, we need to know what the approximate output resistance of the AD8618 is. So without getting into too much detail, we can see from the AD8618 datasheet that the output resistance of the op-amp is less than 100 ohms, since the output impedance versus frequency plot is at most 100 ohms around the unity gain point. It's probably lower than this, but 100 ohms is a good enough starting point. So in our current configuration, R4 equals 0, and thus the pole is at 7.96 MHz, and there is no 0 since R4 is 0. So this is subtracting about 52.5 degrees of phase at our gain crossover of 10.37 MHz, as well as introducing about negative 4.31 dB of attenuation. The process for deciding where the pole in zero should go is not as straightforward as it was for our lead compensation, and since we only need about 14 degrees more phase margin, we should be able to choose somewhat arbitrary values and still meet our requirements. Selecting the value of our ISO to be 100 ohms, just like Z out, will halve the frequency of the pole and introduce a zero at 7.96 MHz. Let's plot it to see what kind of phase we get at 10.37 MHz. Phase is negative 16.51 degrees, which is an increase by about 36 degrees, far more than the 14 degrees we needed to meet our requirements. The attenuation factor is about negative 4.61 dB, which isn't much more than the negative 4.31 dB from before, which means the gain crossover frequency probably won't change that much either. One important thing to note here is that while the loop gain transfer function has this pole zero pair, the actual closed loop transfer function measuring to the right of the isolation resistor has increased attenuation due to the additional 100 ohms of resistance, which is not easy to precisely describe due to the effect of the feedback loop. However, fortunately, neither a pole at 3.98 MHz nor a pole at 7.96 MHz will have much effect on the closed loop gain at 100 kHz. Let's go back to the global loop gain transfer function and see if we've met the phase and gain margin requirements. So now the gain crossover is at 9.99 MHz, with a phase margin of 83.1 degrees and a gain margin of 20.22 dB. So the 100 ohm resistor was actually overkill, and we could probably drop it down by a fair bit and still meet our requirements. But this satisfies all our requirements, and as they say, better is the enemy of good enough, so we'll leave it there. Now the final test is to plot the closed loop gain and the step response. Here we have the circuit set up measuring the closed loop transfer function from the op-amp input Vin to net Vout1 instead of the loop gain. The transfer function looks pretty good. At 100 kHz, there's less than 500 micro dB of gain deviation and less than 1 degree of phase deviation. The 0.1 dB bandwidth is actually at around 1.45 MHz, so lots of margin on our requirements. However, the real test of our requirements is Vin to Vload, since that's what our load is actually seeing. Measuring at Vload, the gain deviation at 100 kHz is 1.13 millidB, so still much better than our requirement. And the 0.1 dB bandwidth is around 937 kHz, so slightly different from the Vout1 measurements, but still much better than our requirement. So we've successfully compensated this op-amp circuit. Let's take a look at the step response pre-compensation versus post-compensation. The pre-compensated circuit in blue rings many times during the step response, whereas the post-compensated circuit in black has no ringing, and very little, if any, overshoot. So we can see that with a few small adjustments, the behavior of the op-amp circuit can be greatly improved with external compensation. I would like to reiterate that in general, op-amp SPICE models are not complete, and in particular, output resistance and input capacitance are often not very accurate. So if you're using a SPICE model to simulate your circuit, I recommend testing it for appropriate output resistance and input capacitance and modifying the circuit to reflect the datasheet rather than just assuming the SPICE model will properly account for these parameters, and doing multiple simulations for minimum and maximum value if necessary. Now that we've done an example, let's briefly look at a few more advanced methods of compensation. I don't have time to go over them in detail in today's video, but we have time to give a quick overview of a few of them. Gain compensation involves directly reducing the loop gain magnitude at all frequencies. Using this circuit, we can reduce the loop gain while preserving the closed loop gain. We can see that at high loop gain, when the ideal op-amp equations are valid, the current through RGC will effectively be zero since VOP plus and VOP minus are equal. And so this does not affect the closed loop gain, only the loop gain. We know that the loop gain is already attenuated by the factor R2 over R1 plus R2, so this equation shows the non-compensated attenuation factor multiplied by the excess attenuation factor due to this RGC resistor. In order for loop gain to be precisely attenuated, Rs must be well known or much smaller than RGC plus the parallel combination of R1 and R2, so this method can be difficult to use if the input resistance is widely varying. Fortunately, this method also works with the inverting configuration, where Rs is usually more easily controlled. And similar to the non-inverting version, the closed loop gain is the same as with the uncompensated version. Direct attenuation of the loop gain is an effective method of compensation for circuits that do not need high bandwidth, as it will push the gain crossover down in frequency and therefore improve phase margin. Note that this equation can get significantly more complicated if the source impedance is not purely resistive. Similar in structure to gain compensation, we can instead introduce a capacitor and resistor to introduce a pole-zero pair, a method called lag compensation. This effectively adds another pole to the system at low or mid frequency, which will cause a decrease in phase afterward, which is then negated by a zero that occurs at a higher frequency. Similar to gain compensation, the point of this kind of compensation is to decrease the loop gain at gain crossover to push the gain crossover to a lower frequency and thus increase phase margin at the expense of bandwidth. The difference is that it doesn't decrease the gain at DC and low or mid frequency, permitting higher precision in that frequency regime due to higher loop gain. Other networks can be put in between the op-amp inputs, and one wonders how well a resistor-inductor circuit would work for high-frequency op-amps, since it would produce a high-frequency zero. You just have to be mindful of magnetic coupling when using discrete inductors in close quarters with sensitive analog circuitry. In-the-loop compensation is a useful method for handling high capacitive loads while preserving output impedance at DC. It's very similar to the isolation resistance method we used on the 808618 circuit earlier, except it's designed to encompass that isolation resistance at low frequencies when both CFB and CL are effectively open, to eliminate the effect of that resistor at low frequencies. It does have a few requirements for the circuit to behave nicely. Both the divider resistance and the load resistance must each be much higher than the op-amp output resistance plus the isolation resistor. And R1 must be much higher than R-ISO. Additionally, the dominant RC time constants for the two poles in the loop gain must be well separated to simplify the compensation. If they're too close together, the transfer function becomes much more complicated, so do so at your own risk. At low frequencies, the circuit looks essentially like a normal non-inverting amplifier. The isolation resistor's resistance, along with the op-amp's internal output impedance, is negated by the high loop gains at low frequency. We'll discuss this effect in more detail in the next episode of the series. At high frequencies, the circuit looks like a unity gain buffer in series with the RC circuit made by R-ISO and C-load, and is very similar to the circuit we compensated in this video, as the lead capacitance we used in that circuit would effectively turn the op-amp circuit from a gain of 2 amplifier to a unity gain buffer just like this circuit. So you size R-ISO based on where you want the pole and zero in the loop gain produced by the isolation resistor and output capacitor to be, just as we did in the example earlier. This circuit can get a lot more complicated if you try to squeeze as much bandwidth as possible out of it, or try to minimize the output resistance over all frequencies, which necessitates breaking the well-separated poles requirement. The larger R-ISO is, the more stable the circuit is, but the larger the output resistance in the mid-frequency regime. The lower R-ISO is, the harder it is to compensate and the more complicated the system gets. I will probably do a video on advanced compensation techniques sometime in the future outside this tutorial series, where I'll have more time to go into these circuits in greater detail. That concludes this episode. In this episode, we introduced the concept of feedback compensation, starting with the intrinsic compensation internal to most op-amps, then moved on to external compensation techniques, applying them to our example circuit, finally ending with a brief overview of some more advanced compensation techniques. In the next video, we will be discussing the op-amp non-ideality of finite output impedance in real op-amps and its impact on op-amp circuits. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have a question or comment, please leave a comment. See you next time.